Question 16. Two electrodes separated by a distance d in a vacuum are maintained at a constant potential difference. An electron accelerated from one electrode to the other gains kinetic energy Ek. The distance between the electrodes is now changed to 1/3 d. What is the gain in the kinetic energy of an electron that is accelerated from one electrode to the other? So in looking at our formula booklet, we're actually going to apply this formula over here because we've got there VE is equal to a half mv squared. Now we know that this is your kinetic energy, your Ek, so that's equal to VE. Just remember, this comes from the idea that from your definition of potential difference, that your V is equal to W over Q. So your work, your energy, work is equal to V times Q, and because we're dealing with an electron, it's equal to VE. And all that energy is put into kinetic energy. Now, when we have a look at this V and this E, nothing has changed. It's got nothing to do with the distance between them. That is not included. So your Ek will still just your energy, your kinetic energy will still just be Ek. Here we have the graph shows the IV characteristics of two resistors. When resistor X and Y are connected in series, the current in the resistor is 2 amps. What is the resistance of the series combination X and Y? So when we have 2 amps, we can use our graph to find the potential difference across each one. So for X, we have a potential, we have 2 amps and we have 4 volts, and R is equal to V over I from our Ohm's law formula. So your resistance is going to equal 2 ohms. And for your Y, we have got this, we have got your voltage there, you've got 2 amps and your voltage is 10 volts. So your R, which is equal to 10 divided by 2, which is equal to 5 ohms. Now, when they are connected in series, we have our formula here. This is for series. When they're connected in series, we just add the two together. So it's going to be 5 ohms plus 2 ohms, giving you 7 ohms. So A is the correct answer. This is always a bit of a trick question, this one. The definition of an ampere refers to. Now, in practice, we think of it in terms of A, but when it's actually defined, the definition is based on B, the force between two parallel current carrying conductors. That is the definition, that is the situation that is used to define the ampere. So one needs to remember that. So that's dealing with our circuit work. Now we are going into the field section, and I will just bring up those formulas there because we may need to use some of them. A spacecraft travels away from Earth in a straight line with its motors shut down. At one instant, the speed is 5.4 kilometers per second. And after 600 seconds, the speed is 5.1 kilometers per second. The average gravitational field strength acting on the spacecraft during this time is. Now, we are told here, do you notice that we are told that it's newtons per kg? Now, if you look here, we have our formula here that G, the acceleration, is equal to force over your mass, which is obviously going to also be a Newton per kilogram. So we're going to be using that, not necessarily that formula, but this is what we're actually trying to find. We're actually trying to find our acceleration. So the gravitational field strength is another name for the acceleration or the deceleration in this case. So what is our acceleration? Well, acceleration is going to equal our final velocity minus our initial divided by our time. So we're going to have 5,100 meters per second minus 5,400 meters per second divided by 600. So we're getting 300 divided by 600. So we're getting 0.5. And when I look at this, I see here I get a 5 times 10 to the negative 1, which is 0.5. So we have got C. 21. A long straight wire carries an electric current perpendicularly out of the paper. Which of the following represents the magnetic field pattern due to the current? Now, to find the direction of the magnetic field for a current in a straight conductor, we use our right hand and we put the thumb of our right hand in the direction of the current. Now, notice here you've got a dot there with a circle. Now, when you have a dot and a circle, that means that your current is coming out. Well, they tell you that it's coming out, but that's what the symbol also means, that your current is coming out of the board. So using your thumb of your right hand in the direction of that, and your curled fingers will give the direction of the magnetic field. So do that and you'll see that you have got D. For this, they are going to be going anti-clockwise. Your curled fingers will go in the anti-clockwise direction. So D is the correct answer.